Welcome to Brain Vision.
All right, so are going back to the Bohr model, and we want to get the de Broglie wavelength for the electron when it's in the n equal 1 level. And so, yeah, I'm trying to think about the fastest way to do this, because I know it's going to be lambda is equal to h over p, and then p is equal to mv. I wonder if I could do it this way. So my goal, okay, is to type in the least amount of things into a calculator, but I know, I'll just say I know I could do P is mv, and then I could use the Bohr model formula for V. I probably should just do that, but I'm kind of curious. So I know L is going to be, it's going to be the square root of 2h bar. Actually, let me rewind and just look at the Bohr model. Well, maybe the interest of time, I'll just do it in the way that's most direct to me. I take back this more complicated approach. So I'm just going to go to V, and maybe, yeah, let's see. Oh, it really is complicated. Well, whatever. Okay. So V is going to be E squared over epsilon naught 2h. So H, so forget this, first of all. I was going to do L as RP, and then because I know L is equal to NH. And then, but then I guess I would still need the Bohr radius. Actually, maybe they list the speed. I think they actually do list it in the text. Oh, yeah, they do. So V1 is 2.19 times 10 to the 6, so fast. So there we go. So H over MB. I'll go ahead and write down that V for you. So that's V 219 10 to the 6. Meters per second. And then mass is 9.11, 10 to the minus 31. So if I go ahead and plug that in and into a calculator, let's see what I get. And so we're going to do this H P. So V is equal to 2.16. Was it 216? 219 10 to the 6. 219 10 to the 6. And great. So with that, I get 0.332 nanometers. And we want to get, how does that compare to the, we want to get for n equal 4 as well. So we can see in the text that velocity goes as 1 over n. So n is 1 to n is 4. So for n equals 4, it's going to be going 4 times slower. So that's going to, so if v goes to v over 4, then lambda is going to go to 4 lambda. So then, so just mark this. This is n equal 1. And then n equals 4. We're going to do 4 times that. So we're going to do this whole thing times 4. So 1.33 nanometers. I was just excited about the next part, I think. And I wrote it in 2 different ways. Haha. Nanometer and 10 to the minus 9. Okay, and then we want to compare it to 2 pi r of the orbit. So for 1, maybe I'll kind of make like a little n equal 1 zone. So r is going to be, or 2 pi r, I should say. So r is this 0.5 10 to the minus 10. So that's one I actually have memorized. 2 pi r. That's supposed to be a pi. So I'm going to go ahead and evaluate that. 2 times pi times 0.52. I think it's 5293 10 to the minus 10. Let me see if that's right. I'm going to check the textbook. 5293 10 to the minus 10. Wow. Really stored that in my long-term memory. And that is 3.33 10 to the minus 10. And so yeah, so they're actually the same. So how convenient. And then I think it's going to end up being the same here, because what happens to R according to formula 28.13, R is proportional to n squared. So R is going to be 4 times the original, goes to 4 times R1. So R goes to 4 times R1. And I'll call this R1 just to be totally clear. And then V, oh yeah, and then R goes to 4 times R1. And then we already saw that lambda went to 4 times lambda. And so we can say if we multiply this by 4, we expect to get this multiplied by 4, which is this. So it should be the same. So you can kind of get this picture. I wonder if they have it in the text. Or basically, like, you can make the de Broglie wavelength sort of go like this. I mean, that's not right. That's like a few different wavelengths. But you can like take a sort of sine curve and like spread it out. And then with each increase, you like add in an extra wavelength. So it's not exactly, the Bohr model isn't really true, but it really does speak to something there with energy levels. And yeah, but it's kind of an interesting piece to think about.